Welcome to today's explainer. Let's just jump right in. I want you to imagine we're sitting down together, whiteboarding our next enterprise AI architecture. I'm taking you under my wing today to talk stack design because we have a massive opportunity here. But to actually get there, we've got to solve literally the biggest bottleneck in AI right now. We fully expect our agents to handle these complex, multi-session, long-horizon tasks, right? We want them coding, trading, managing workflows for weeks or even months. And yet, they constantly forget crucial details. They completely fail to genuinely adapt to our preferences. Every time a new session starts, it's like they've got total amnesia. There's this great quote from Nobel laureate Eric Kandel. "We are who we are because of what we learn and what we remember." And honestly, that perfectly captures our mission today. Our AI absolutely shouldn't just be a glorified information retrieval engine. It needs to genuinely learn. It has to internalize experiences directly into its neural pathways, just like human memory, instead of just running basic database lookups.
So here's our roadmap for this explainer. First, we'll hit the limits of frozen models, then dive into the fast weights revolution. After that, we'll look inside the TMM architecture, break down the math behind SVD initialization, compare static versus self-evolving agents, and finally wrap up with enterprise ROI and future impact.
All right, part one, the limits of frozen models and why context windows and external databases just aren't cutting it anymore.
Let's contrast how these two approaches actually handle data. If your agent is purely relying on traditional RAG, retrieval augmented generation, it is essentially doing a keyword search in a pinned Discord channel. You know how clunky it is when users complain about filtering pinned messages just to find a true or false answer? That is exactly what our static agents are stuck doing. It's clunky, it's incredibly slow, and the agent itself hasn't learned a single thing. We really need to shift to active, real-time parametric model evolution, where the agent fundamentally internalizes the experience. Think about it. Static models just look up past experiences. They don't internalize them. So when a frozen model gets a long horizon goal, you're forced to cram raw, noisy histories into the prompt, which drives up attention costs like crazy. Plus, managing external databases introduces massive latency and demands constant manual maintenance of those external indices. And the biggest risk? If your external summary accidentally omits even a tiny piece of evidence, it is permanently lost to the agent. It fundamentally fails to adapt in real time to shifting user preferences. Which brings us to part two, the fast weights revolution. How we are shifting from static retrieval to active parametric evolution. By leveraging parametric memory, what we often call fast weights, the agent actually writes useful experiences directly into its own parameters at test time. It uses lightweight online LoRa updates to absorb supervision. So instead of eating up precious prompt space or waiting for an external database to return a semantic match, the model fundamentally alters its own future behavior in a single episode. It's a total eureka moment. It's the difference between reading a manual every single time you want to ride a bike versus actually knowing how to write it.
Let's move to part three, inside the TMM architecture. This is the framework for self-evolving agents. As your lead engineer, this is the stack I need you to completely understand.
Think about the flow of information here. Once the working context budget hits its limit, the agent doesn't just write a lossy summary and dump it into a vector database. No, it distills the history into explicit memory and then absorbs that supervision straight into fast LoRa weights through an active learning loop. The policy itself is literally changing in real time.
Part 4. The math. SVD initialization, accelerating convergence, and preventing amnesia.
If we're going to constantly update weights on the fly, we absolutely have to figure out how to do it without destroying the model's pre-trained brain. Standard LoRa updates normally start from a random Gaussian subspace, which just wastes tons of computing time trying to find the right direction to learn. Singular value decomposition, or SVD-based initialization, completely fixes this. It's a mathematical technique that anchors our online updates directly to the most important, high-energy directions of those pre-trained weights. The mathematical advantages of updating low-rank weights like this over full model fine-tuning are huge. By deriving the projection matrix from the SVD, we can actually freeze the A matrix to save compute, and only update the coefficient B matrix online. This acts as an adaptive preconditioner. It accelerates convergence in just a few steps, achieves lower approximation error, and beautifully prevents catastrophic forgetting across multi-session interactions. Now, just to put modern system speeds into context, traditional memory indexing structures allow for semantic search speeds around 100 microseconds. Pretty fast, right? But parametric memory takes that efficiency to a whole new level.
By internalizing the knowledge straight into the weights, we bypass the computational cost of continuous database lookups entirely. This allows the agent to naturally reason over its learned experience with literally zero retrieval latency.
All right, Part 5, Static versus Self-Evolving Agents, where we prove the performance trade-offs.
Let's walk through a step-by-step example comparing the two. Consider what happens at Step 3. When the context budget is triggered, the static agent is busy desperately trying to cram a lossy, shortened summary back into its prompt window. But the TMM agent? It distills the session into QA-style supervision and applies an immediate, lightweight update to its fast weights. By Step 5, the TMM agent has already fundamentally evolved its core policy for future tasks, natively handling dynamic data, while the static system is still just reading its old notes. And the benchmark data backs this up undeniably. On the LongMem eval-s benchmark, using an 8 billion parameter model, TMM massively outperforms traditional summary and retrieval baseline architectures. We're talking about a 46.2% F1 score. That is a massive 10-point gain over the absolute best retrieval-based methods. It definitively proves that internalizing experience flat-out beats simple retrieval.
Now, pacing is everything here. The effect of the context budget actually forms a clear bell curve. If you trigger the memory extraction too early, you aggressively compress the data and lose those crucial fine-grained details. But if you wait too long, the prompt becomes way too noisy to actually learn from. Finding that exact sweet spot is absolutely key to optimizing online learning performance.
Finally, Part 6, Enterprise ROI and Future Impact. The business case for the product managers tuning in. Let's translate this raw architecture into long-term operational efficiency.
Think about the real-world scenarios where immediate learning drives the most value. A financial trading algorithm has to adapt instantly to noisy shifting markets. It absolutely cannot wait for a nightly database rebuild. Or picture a customer service agent that actually remembers nuanced, multi-session preferences in real time. We're talking about code generation agents patching their own reusable skill libraries and successful workflows propagating autonomously across entire swarms without a human ever writing a single new rule.
The long-term enterprise cost savings here are just astronomical. You are fundamentally eliminating the manual overhead of constant prompt engineering and external index maintenance. By making the switch to self-evolving agents, you drastically slash the compute costs associated with processing massive bloated context windows. And most importantly, it drives higher task success rates because it completely mitigates that dreaded agent paralysis loop, where static systems just keep repeating the exact same failed actions over and over because they can't adapt on the fly. Because the TMM system fundamentally co-evolves its capabilities with its experiences, its knowledge compounds exponentially over time. I love this quote. Within 30 days, the agent will likely know more about your client's specific winning patterns than a junior employee who's been there for a year. That right there is the true power and massive ROI of parametric memory in the enterprise.
So, I want to leave you with this final provocative thought to take back to your product teams. When you sit down to architect your next system, are you building an AI that just clumsily searches for answers in an external database? Or are you building an agent that actually internalizes and learns from them? Thanks for joining me on this explainer. Keep learning, and I'll catch you in the next one.